Okay, if you remember, just after that long weekend and the exam before that, so we're going back a full week. Seems like a year, but it's only a week. We had solved over the course of the semester, for example, 2 CSTRs in series. And what we found when we did the Laplace transform was CA1 prime tilde, that is the exit, if I only had a single reactor and have a reaction A goes to B, first order. Then what we found is that CA1 prime tilde was KP1 over 1 plus ST1 times CA in prime tilde, where Kp was big T over little t, which is 1 over 1 plus K tau. When we have 2 CSTRs in series, we have the same thing for CA2, but what's coming into reactor 2 is CA1, not CAN. So CA2 prime tilde, which as in analogy to this, was Kp2 over 1 plus ST2, CA1 prime tilde, where Kp2 is just the same thing as this, where I is equal to 2. And then when we plug in CA1 prime tilde into this expression, we get Kp1 plus 2, which is the product of Kp1 and Kp2. This is just the product of those two. Over 1 plus ST1, 1 plus ST2 times CA in prime tilde. The nice thing about this is you can see that since both these, both individual reactors, because they have a first order reaction, the equation for those reactors were linear. So therefore, we're able to eliminate the intermediate. That is, we're able to write CA2 prime tilde solely in terms of CA in prime tilde without CA1. We're able to eliminate that. And you can only do that with linear systems. If you remember, if we had a nonlinear reaction here, then when we linearized it, we would have information about the intermediate in big T. So we wouldn't be able to eliminate the information about the intermediate, CA1. But because this is a first order reaction, we are able to eliminate that. And we're going to mine that over the course of this and future classes, that when systems happen to be linear, that's really nice because we can write the output in terms of the input, the outputs in terms of the inputs, and eliminate all the stuff in between. We still have to do the work to figure out how to do that, but that we can do that is a result of the fact that the system is linear. And of course, notice the way I did this, I didn't have to specify what CA in prime tilde was. It could have been a step, it could have been a pulse, it could have been anything. This is still the right example. I just have to plug in for CA in prime tilde. Here I wrote 2 examples of that. Just stuff we'll be referring to over the course of the hour. Remember, there was a duality between S and T in the sense of the initial and final value theorems. The final value theorem, if we want to know the limit of f as t goes to infinity, if it's a steady state, for example, if this limit exists, then this limit exists. The limit of s goes to 0 is at sf tilde. Similarly, so t goes to infinity corresponds to s goes to 0 under the case where f is continuous. And similarly, the initial condition says t goes to 0, the initial condition of f corresponds to s goes to infinity of sf tilde of s. Finally, a couple of definitions. Over the course of the semester, we've defined the steady state gain, Kp. And Kp, we know, is the limit as t goes to infinity of the change in the output over the change in the input. Obviously, this makes the most sense if I'm dealing with a step function change. If I don't have a step function change in the input, what am I talking about? I don't know. This makes the most sense. This makes sense in terms of a step function change in the input. What happens to the output at steady state? Now, of course, so there are 2 things here. One is I'm assuming a step function change in the input. And 2, I'm assuming that the output reaches steady state. What we know is when systems are unstable, that may not happen. So in order for Kp to make sense and to give me a finite number, I need the output, I need the system, or the output, to reach a steady state that is the same or different from the initial state. And finally, at the end of the last hour, before the exam, we defined this G tilde of S, which we gave it a name to, which of course I forgot. Transfer function, thank you. We call it the transfer function. And we said the definition of the transfer function, and I should put colons here because these are definitions. Colon and an equal sign is a definition. It's the Laplace transform of the output over the Laplace transform of the input, assuming the initial condition is 0. You make the initial condition 0 by working with prime variables instead of with unprime variables, because the initial condition of the prime variable is 0 by definition. So let's just look at some examples of transfer functions. Let's look at G tilde of S for one CSTR with A goes to B. Well, that's the change in, we said it's the Laplace transform of the output of the Laplace transform of the input. Here's the output, here's the input. So it's CA1 prime tilde over CA in prime tilde. And that's just 1 over 1 plus ST1. Right from here. How about for example, G tilde of S for two CSTRs in series with the reaction A equals to B. Well, that's CA2 prime tilde over CA in prime tilde. That's CA2 prime tilde over CA in prime tilde. Well, that's just equal to KP 1 plus 2 over 1 plus ST1, 1 plus ST2. So notice, so that's interesting. And let's do another one, just for fun, which might look familiar to you because it's something I asked you in the exam. So let's assume, so this is example 1, example 2, example 3. And example 3 is, let's say I have a CSTR with A goes to B. But at t is equal to 0, both the volumetric flow rate takes a jump, and also CA in takes a jump. So they're both taking jumps at the same time, both at t is equal to 0. I have to do this on the exam. So let's just, so here I have a V coming in, CA in, CA coming out, and obviously isothermal, assuming constant uniform density. So let's just set this up. So I have dCA dt is equal to the basic CSTR equation, is little v over big V times CA in minus CA minus KCA, because I'm given this as a first order reaction. Look familiar? Okay, so now we have to go through our steps. Our first step is to write the exact equation for t greater than 0. This is exact. And now we need to identify what's changing. So what's changing here? I need your help. This is not a monologue. Little v is changing and CA in is changing. Now those are inputs that are changing. Are there any outputs that are changing? CA. So everything's changing. So let's notice there's only one blue in this term, so it's linear. There's only one blue in this term, it's linear. But this term and this term are both nonlinear. So I need to linearize them. So this is nonlinear. So I can use blue chalk to make it maximally invisible on a blackboard. So let's note that V over big V, CA in minus CA. I can consider this right now, I'm doing both terms at once. So this is equal to, I'm going to use a sub S for steady state, I'll use a sub 0 for the initial condition. So this is V0 over V, CA in 0 minus CA 0. So remember, I'm appealing to F of xy is equal to F of x0, y0, plus the F dx at 0, x minus x0, plus df dy at 0, y minus y0, plus nonlinear terms. So this is f of x0, y0. I'm going to let this thing be f, and this thing be, this thing be x, and this thing be y for here. So now I take df dx is ddv of this thing. ddv of this is just that. So it's 1 over big V, ca in 0 minus ca in 0. Evaluate at 0 times x minus x0 times v prime. And now I need df dy. df dy is the derivative of the product with respect to this term. So I just get little v over big V. Evaluated at the 0 point times y minus y0. That's ca in prime minus ca prime. Plus nonlinear terms. And L is nonlinear. Okay, so here I have the exact formulation for t greater than 0. And now we're going to do the linearized for t greater than 0. And that's just equal to dca dt. Is equal to, well, this guy, which now I write these three terms, v0 over v, ca in 0 minus ca 0, plus plus ca 0 in minus ca 0 over big V minus v prime, plus v0 over v, ca in prime minus ca prime. So these three terms I just got from here. I just took this term, I replaced it by the sum of these three, linearization, and this comes along for the ride, minus kca. Clear? Just following the steps. Exact t equals greater than 0, linearized t greater than 0. Now I do exact t equals to 0. Well, t less than or equal to 0. So that's dca 0 dt, because 0 is what was happening at time t equals 0. And that's equal to v0. I just go into this equation with all zeros over v. ca in 0 minus ca 0 minus k ca 0. That's just this equation with all zeros. And now I subtract the two. dca dt minus dca 0 dt is ddt of ca prime. This term is exactly the same as this term. They cancel. This term, so this term, now I have ca0 in minus ca 0 over v prime. That comes down. Here I have v0 over v ca spread over v prime. v0 over v ca in prime minus ca prime. That came down. And now I have kca and kca 0. That's just minus kca prime. Clear? Just following the same steps I always do. Now I notice I have two ca primes on the right. So I need to bring those terms to the left. So I have dca prime dt plus kca prime. And this thing is just big V over little v is just tau. So I can write this as ca prime times 1 over tau 0. And that's equal to ca0 in minus ca0 over v prime plus v0 over v ca in prime. And now I do the usual. This is, I can just write as 1 plus k tau 0 over tau 0, which I write as 1 over t0. And now I Laplace transform. And I have S plus 1 over T0 times CA prime tilde. Because this gives me S CA prime tilde, and this gives me CA prime tilde over T0. And that's equal, which I can now rewrite as 1 plus ST0 over T0 times CA prime tilde. And that's equal to CA0 in minus CA0 over V prime tilde plus V0 over V CA in prime tilde. And now I just solve for CA prime tilde. So that just means I multiply by T0 over 1 plus ST0. CA0 in minus CA0 over V. V prime tilde plus T0 over 1 plus ST0. V0 over big V. Times CA in prime tilde. I did a lot of algebra there, but it's algebra that hopefully you were able to do exactly the same algebra when you took the exam. It may have taken you a few more steps, so I did it maybe the most direct way. But it's again following the formula or the protocol we've been using all semester. Exact for t greater than 0, identify the nonlinear terms and linearize them. Write the linearized equation for t greater than 0, write the exact equation for t less than 0, subtract them, and rearrange. Get all the CA primes on the left, everything else on the right. The reason I write it this way is you can see that here I have the two things that are driving. These are the driving forces for change. That is, there was a change by hypothesis, there was a change in V and a change in CAN. It's the V prime and CAN prime. They're on the right. On the left, I have CA prime tilde. So notice I can, in terms of G tilde of S, the transfer function, tells me how the outlet in Laplace space reacts to the inlet. So here I have two G tildes. I've got a G tilde which tells me how V prime affects CA. And that's just equal to T0 over 1 plus ST0, CA0 in minus CA0 over V. And I also have a G tilde of how CA in prime affects CA prime. And that's just equal to T0 over 1 plus ST0 times little v0 over V. Now right now, I just calculated these G tildes. We haven't yet seen the significance. We'll see that in the next few minutes. I'm not going to put that off forever. That's what we're going to see here. But first I just want to show you how to calculate these G tildes, and then we'll see why they're so interesting. Right now they're not interesting. They're just a nuisance because we have to calculate them. But they will become interesting. I promise. Let's notice that if you remember these expressions here, CA2 prime tilde had a bunch of stuff that depended on the system, and then it had the input. Because remember the 1 plus ST1, the 1 plus ST2, where did that come from? The 1 plus ST came from the derivative on the left and the output on the right. And basically these things, these outputs, were characteristics of the system. Notice they don't have the forcing function. The forcing functions, V prime and CA in prime, stay on the right. So what are we getting in CA2 prime tilde? We have all this stuff here which came from the system itself. It came from the time derivative, it came from the reaction, and it came from the outflow. It didn't come from the forcing functions, V prime and CA in prime. So I can change the forcing functions, and I don't change this part. And we'll see how that is useful. As we're going to see, the system, not the forcing functions, is what determines the stability. We'll see that the stability is, all the information about the stability is in the system, not the forcing functions. So that's really nice, is that when we get this G tilde, already it's sort of coming attractions, the G tilde factors out it divides out the input information. So the information about, it's the output over the input. And that should contain all of the information we're going to need for the stability analysis, as we will see. Any questions on that yet? Much of what I just said in the last 2 minutes after I stopped writing is stuff that I'm going to make clearer with examples as the hour goes on and with more explanation. So don't worry if you didn't catch every little comment I made. Those, when you listen to this afterwards, you know, when you can't sleep at night and you listen to the recording, it's all going to make sense to you. Questions? Okay, so what's next? So now a couple of simple definitions. Now that we have this transfer function G, we can talk about the order of G tilde. The order of G tilde, and again, I'm always assuming that I've canceled out like factors from the numerator and the denominator. So that's a given assumption. And the order, we're talking about is the highest power of S in the denominator. That's called the order of the, and the poles of G has nothing to do with the country of a similar name. The poles of G are defined as the roots of the denominator. And finally, the zeros of G tilde of S are the roots of the numerator. The roots of the numerator. So these are just words now, and we'll talk about the significance of these words as we go along. Okay, so one thing is we know that information about stability has to do with the denominators. Remember when we did our analyses of stability, we looked at the denominator because everything that looks like a 1 plus st, when we go back to the time domain, looks like e to the little t over big T. So when we invert 1 over 1 plus st, we get e to the minus t, e to the little t over big T1. So obviously the sign of t of big T1 makes a difference. Notice that's the root of this denominator, or the, what do we call it, the poles of the denominator here. The poles are the zeros of the denominator. Here a 0 is minus 1 over T1, and another one is minus 1 over T2. That's the values of S that make the denominator 0. So we see that the poles of G give me information about stability. The numerator doesn't really, as we're going to show now, doesn't tell us us anything about stability, but it does tell us what happened, what the trajectory is. It's important, the numerator, but it doesn't tell us anything about stability. But not stability. And let's see why that's the case. Well, if you remember, we want to look at that. So in order to look at that, let's notice that y prime tilde. So I'm going to call the output y. Let's call this y prime tilde and x prime tilde. So I don't have to keep writing words. So I don't have to keep writing in and out. I'm going to let y represent out and x represent in. So I have y prime tilde is equal to g tilde of s times x prime tilde. And notice, whenever I make a tilde over something, it's in the s domain. That's just my shorthand. Not just mine, it's just a typical shorthand. So that way, sometimes I may forget to write the parentheses s, but as long as you see a tilde on top, you know it depends on s. And conversely, whenever you want something to depend on s, it's a good idea to put a tilde on top. So that way we're consistent with notation. Okay, so this is going to have, remember, this is going to have, if I want to invert this, this is going to have some numerator over some denominator. And it's going to have some roots. So for example, we said, let's say I have a simple pole. If I have a simple pole, then this would be m tilde, mi tilde of s over s minus si. I could write it that way. And we had a formula for mi. We said we could write this as c, let's call this 1, make it a little easier. C1 over s minus s1 plus some remainder tilde of s. And we went through that in great detail, but I want you to notice that C1, we said, was equal to M1 tilde of S1. In the case where we have some pole. So notice that this is N tilde of S1 divided by D tilde of S divided by S minus S1 evaluated at S1, where we just take out that factor, and if it's a simple pole, D tilde of S1 divided by S minus S1, when I evaluate it at S1, I don't get 0. Because if I did, I would have another factor of S minus S1 in there. And I'm assuming I don't, by assuming it's a simple pole. So what you can see here is that the numerator contributes to the coefficient. So the numerator is important. It tells me what the coefficient is. But when I invert this, I get C1 e to the S1t. Or maybe with a minus, I don't recall. I think it's e to the S1t. So when I invert it, so what happens, when I'm looking at the time dependence of the system, the time dependence, which is the exponential, coming into the exponential, is it going to blow up? Is it going to decay to a steady state? Is it going to oscillate? What is it going to do? That all depends on S1, and S1 comes from the denominator. It doesn't come from the numerator. All the information about stability came from the denominator. That doesn't mean the numerator is irrelevant. The numerator is important because it's important in determining C1. It determines the coefficient, but not the stability information. And here I did this as an example for a simple pole. The same argument holds for the multiple poles or for the complex poles. It's the exact same argument. Are there any questions on that? Okay, now comes something slightly more philosophical. Don't get scared. A little philosophy isn't so bad. There's a notion of in physics, and of course everything we do is a special case of physics, called causality. And the notion of causality says what happens in the present can depend on the past and the present. It can't depend on the future. That is, how I do on the test today can't depend on the material I'm going to learn next year. It can only depend on what I know now and what I learned in the past. Makes sense, right? And that's a principle in physics. So how does that come in here? Well, we say that G tilde of S is strictly proper if the limit as S goes to 0, so G tilde of S is 0. So it's strictly proper if the limit is 0. But what does that mean? Well, let's remember that means the limit as S goes to 0 of G tilde of S. Well, G tilde of S is Y tilde prime over X tilde prime. Limit as S goes to 0. Well, the first thing it's telling me is that the only way the limit can be 0 is if I have more, if the highest power of S in the denominator is bigger than the highest power of S in the numerator. So this tells me that the highest, it's sufficient. If I have polynomials, if n tilde of S and d tilde of S are polynomials, then the highest power of S in d tilde of S must be bigger than the highest power of S in n tilde of S. That's necessary and sufficient. Is that clear? If I want the limit to go to 0, I better have more S's in the denominator than I have S's in the numerator. Did I do that right? I think it's S goes to infinity. Let me just make sure. It's 0 infinity. It's S goes to infinity, I'm sorry. It's S goes to infinity. So let's review. It's the limit as S goes to infinity of G tilde of S. And I'll get back to this in a second. But if I have a polynomial, a ratio of polynomials, when S goes to infinity, if I want the ratio to go to 0, I better have more S's in the denominator than the numerator. Otherwise, that won't happen. Plus. So clearly, strictly proper, if I have polynomials, tells me I have more powers of S in the denominator than the numerator. Let's just see where those powers of S come from. Remember, where did the powers of S come from in G tilde? The powers of S came from, let's say here, this power of S in the denominator came from the DDT. It came from the DDT. This came from the DDT in the first reactor. This one came from the DDT in the second reactor. So the time derivatives on the left gave me S's for the denominator. Where would I get S's from the numerator? I would get S's from the numerator from forcing functions. But the forcing functions are talking about now. They're not talking about the future. They're what just happened. So I'm not getting more powers in the numerator because of causality. Because I'm only talking about things that happen now, not in the future. If I were talking about what was going on in the future on the right, if I had something that happened tomorrow changing, causing a ddt now, then if you remember, the Laplace transform of a delay was e to the minus s theta, e to the minus st. So therefore, this is a delay. So the future influencing the past would mean I would need an e to the plus st. So I can't have e to the plus st in the numerator. And this would give me lots of powers of s in the numerator. I can't have that. Okay, now why don't we look for a second at proper. Yeah, so let's look at this thing. Let's look at that limit. Let's say, what if x prime is a set? If x prime is a set, then this is equal to the limit as s goes to infinity of y prime tilde divided by, what's x prime? Well, if x prime is a set, then x prime tilde is the change in x over s. Times s, if it's a step. And now we can use the initial value theorem. The limit of s f tilde is the limit as t goes to 0 of f of t. So notice this just has a 1 over delta x times the limit of s times y prime tilde as s goes to infinity. That's just equal to y prime of 0. So requiring this to be 0, requiring it to be 0, says that initially there's no change in y. That I can't have a change in y due to a change in x before I have the change in x. I can only have that after t goes to 0. When I change x at t equals 0, nothing is changed yet in y until t is greater than 0. So it's again another statement of causality. Is that clear? The future can't influence the past. The past can influence the present, the future, but not the other way around. Do you have any questions on that? Again, the notion of causality makes a lot of sense, and we just want to see what that notion tells us about G tilde, forms of G tilde that are allowable. Because if I had a form of G tilde that didn't satisfy this, I know there's something wrong, because that's telling me the future is influencing the past, or the present. And that's, so therefore, if I ever do a calculation, say on an exam, or more importantly, in a job, and I get a G tilde that doesn't satisfy that, I know that's a red flag. Like my shirt, it's a red flag. Something's wrong. Gotta fix it. Okay, so again, let's just look at a simple example. Let's look at the two CSTRs in series. We know that G tilde, I have it over here. The G tilde, I know that the poles are s is equal to minus 1 over t1 and minus 1 over t2. So the poles of G tilde are giving me exactly the information for stability. They're giving me information for stability. Let's apply the final value theorem to this. The final value theorem says the limit as t goes to infinity of CA2 prime of t is equal to the limit as s goes to 0 of s CA2 prime tilde.
Professor,
Yep.
will you read what you hold for s?
I'm sorry?
Will you read out loud the rule for S?
Yeah, I wrote the poles are S is equal to minus 1 over T1 and minus 1 over T2. Because I'm looking at the poles of this are the zeros of the denominator. If I say 1 plus ST1 equal to 0, and I solve for S, I get minus 1 over T1. If I say 1 plus ST2 equal to 0 and solve for S, I get minus 1 and bring the other side over T2. And those are the two solutions. Is that clear? So the limit is S times CA2 prime tilde. Well, again, I don't need the initial condition because I'm using prime variables, so the initial condition is 0. So this is equal to the limit as S goes to 0 of CA2 prime tilde. CA2 prime tilde I have up here somewhere. Here it is. It's KB1 plus 2 over 1 plus ST1, 1 plus ST2. Anything out? Times CA in prime tilde. Times CA in prime tilde. And let's see what CA in prime tilde is. Depends what we have there. If this is a set, and I have to multiply by S. So if it's a step, then this is delta CA in divided by S. So let's see what I get here. If I have a step, then the S is canceled. Well, let's do, if it's a step, where CA in prime tilde is equal to delta CA in over S, then the limit as t goes to infinity of CA2 prime of t. Well, the S is canceled, and I'm left with delta CA divided by, well, times KB 1 plus 2. And when I think limit as S goes to 0 of this, I get 1 and times 1. 1 times 1. So I just get, so this tells me that CA2 prime is the same as delta CA2 over delta CA1 as t goes to infinity, which is exactly my KP, is in fact equal to KP 1 plus 2. So what I'm showing from here is that from this calculation, we find that CA2 prime tilde over CA2 prime of infinity over delta CA in is in fact KP 1 plus 2, which we knew already. We knew that from direct calculation, but here it comes out of the final value theorem as well. What happens, on the other hand, what if CA in prime is equal to some k, well, let's call it alpha, times delta t. It's pulse. Then the limit as t goes to infinity of CA2 prime of t is equal to the limit as S goes to 0 of S times KT 1 plus 2, 1 plus ST1, 1 plus ST2 times CA in prime tilde. Well, that's just equal to alpha times 1, because the Laplace transform of a pulse is just a constant. And let's call the constant alpha instead of k, because I'm using k for steady state gain. It's just the amount of A I added. So in this case, when I take the limit as S goes to 0, this still becomes a 1, this becomes a 1, but I have an S sitting here in the numerator. Limit as S goes to 0 is 0. And that's correct, because if I have a pulse in two CSTRs in series, then the output, CA, might go up, but it's eventually going to decay back to 0. for two CSTRs in series. We showed this earlier. It eventually goes back to 0. It forgets the pulse, because the pulse happened to equal 0 and ended at equal 0, and eventually the system forgets it. So that's just using this formalism in a way that tells us stuff we kind of knew already. Any questions on that? Okay, questions? Well, that brings us to block diagrams. What are block diagrams? Well, why do we use diagrams? A lot of times when you have algebra, you can get lost in the algebra. We've all had that problem, we get lost in algebra. But sometimes if you can represent the algebra in a one-to-one manner with pictures, it's a lot harder to get lost. In fact, so for example, you may have heard of the great physicist Richard Feynman. And what Richard Feynman got his Nobel Prize for in physics was he was doing calculations in quantum electrodynamics, so the physics of light, for example. And the algebra was a real mess. Could take pages and pages and pages. And what he found was you could represent that algebra exactly with pictures, with little diagrams. And you could do the algebraic manipulation with the diagrams, get the answer, and then translate it back into an equation, and you always got the right answer. Now that wasn't why he got the Nobel Prize, but that made those calculations much more doable. And there are many areas where diagrams substituting for algebra, if it's an exact substitution, allows you to do many steps of the algebra simply and exactly, and then you translate it back to equations. So that's the basic idea. So I want you to notice that when we have linear systems, we can write the output as a function of the initial condition, G tilde of S, and the forcing. So those are the three elements, the three ingredients. The output depends on the input, the initial condition, the forcing, what happens for t less than 0, the forcing, V prime, C in prime, and G tilde. Because remember, Y prime tilde is G tilde times X prime tilde. Here's the transfer function, here's the forcing. The only thing I'm missing is the initial condition. So that's true. And let's just write some blocks. And remember again, with linear systems, we have this nice thing that we can eliminate the intermediates. We could write the outputs in terms just of the inputs, G tilde, and the initial condition, not the intermediates. So if I have 10 CSTRs in series, I could write the output of CSTR 10 in terms of the input to CSTR 1 and not have to write out CA 1 through CA 9. So there are some sort of rules for this, simple rules. And so here are the basic rules. So if I have an input, so this is good and this makes sense, makes sense. And this is nonsense. So if I have an input, X prime tilde, and a G tilde here, and a Y prime tilde, this makes sense, because this is a way of representing Y prime tilde as equal to G tilde X prime tilde. That makes perfect sense. On the other hand, this one doesn't. This one makes no sense. This makes no sense. I don't know how x1 and x2 combine with a single G to make Y. So this is nonsense. and this makes sense. The second thing, so I can only have one input to a G box. Another thing that makes sense is if I have x1 and x2. This is a way of writing. This is a diagram for x3 tilde is equal to x1 tilde plus x2 tilde. So that makes perfect sense. That's the way I write that. And similarly, if I have another one, I can have x1, x2, x3. Here I'm combining two streams. Here I'm breaking up a stream. This is another way of writing x1 is equal to x2 is equal to x3. Those all make sense. How about things that don't make sense? This doesn't make sense, neither does this. I have no idea how x1 has been broken up by g into a y1 and a y2. That makes no sense. Makes no sense. Similarly, I can't do this. I can't. I can't multiply x's. I can only add them in block diagrams. So these are nonsense. Don't ever do them. Bad. These are good. And how do I interpret a block diagram? I interpret it, as we'll see, going from the end to the beginning. So let's look at a simple example. Let's say I have n CSVRs in series. So here I have CA in, CA1, CA2, CAN, CAN minus 1. So I want you to notice that G1 tilde is equal to CA1 prime tilde over CA in prime tilde. G2, by definition, is the outlet for reactor 1, it's reactor 2. It's the outlet of reactor 2, CA2 prime tilde, over its inlet, CA1 prime tilde. And in general, CAJ prime tilde, GJ tilde, is equal to the output from reactor J, CAJ prime tilde, over its input, J minus 1 prime tilde. So let's write CAN. So G for the whole process, N CSVRs in series. That's equal to CA n prime tilde over CA in prime tilde. That's equal to, I'm going to multiply and divide by stuff. That's CAN prime tilde over CAN minus 1 prime tilde. CAN minus 1 prime tilde over CAN minus 2 prime tilde. Dot, dot, dot. CA2 prime tilde over CA1 prime tilde times CA1 prime tilde over CAN prime tilde. Where all I did was I multiplied and divided by CA1, CA2, dot, 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 CAN minus 1. But this is just GN. This is GN minus 1. G2, G1 tilde. So immediately I have that G tilde for the whole thing G1 tilde, G2 tilde, dot, G3 tilde. And I can represent this by a block diagram. I have CA in coming in here, and this is G1. This comes out as CA1 prime tilde, and goes into 2. What comes out of that is CA2 prime tilde, that goes into G3. Goes into Gn tilde, which I have CAN prime tilde, CAN minus 1 prime tilde. Is that clear? So notice that this is going to correspond to that because CAN prime tilde is GN CAN minus 1 prime tilde. CAN minus 1 prime tilde is GN minus 1 CAN minus 2 prime tilde, and N minus 1, etc. Eventually, I get to G1, which is CA1, which is G1 with G1 is CA1 prime tilde over CA8 prime tilde. So I have this block diagram corresponds to the NCS Torsen series, and I extract this from it. So why don't we do a couple more examples on that? Let's look at another example. Let's look at G1 tilde, G2 tilde. So here I'm going to have x1, x2, x3, y1, y2, y3. And I need your help. I need your people here helping me with this. And again, in class, some people are shy and they don't like to volunteer. But you know, if you volunteer, you get to learn. Because it's okay if you make a mistake, but you get to see what your mistake is. If you sit there quiet and you don't volunteer, then you might miss it. You may never get it. So don't be shy. Now the way you do these things is you start from the end. And here are my rules. So first thing, my goal is to write y3 in terms of x1. The goal is to write y3 prime tilde only in terms of x1 prime tilde. But I need to get there. So you start at the end and you work backwards. So the first operation I have here is y1 and y2 coming together to form y3. So what does that tell me about y3? What is y3 based on these pictures here?
Is y1 plus y2?
By item 2, it's equal to y1 plus y2, because this part of the picture looks exactly like this. So that's equal to y1 plus y2. Okay, but now I need to go to figure out how y1 relates to x2 and how y2 relates to x3. So what does this part of the picture look like? Somebody else. Somebody else. First one. So that tells me that y1 is equal to g times x, g1 times x2. And y2, it's the same thing, is g2 times x3. Okay, but now I need to know, okay, what is x2 and x3? How do they relate to x1?
They're equal.
They're equal because of figure 3. So x2 and x3 are the same. So this is just g1 tilde equals g2 tilde times x1 tilde. And that's what I wanted. I want y3 tilde in terms of x1 tilde. So you see, this is not hard. It's just a matter of getting used to it. Let's do one that's a little more interesting. And this is going to be the first time we use feedback in this class. So let's say I have this. read the picture correctly. I know I'll stick something else in there. Okay, so here I have y, here I have an x, call this y, and then I'll give these numbers. 1, 2, 1, 2, 3, 4. So that looks complicated, doesn't it? Well, again, don't get scared. The goal is to write y2 tilde as a function of x1 tilde. Output, input. This is the black box. It has feedback because the output is going and influencing the input. So let's start out with y2 tilde. Let's just look at this part of the picture. I've got y1 going and splitting into y2 and y3. Which one of these three does that look like? Somebody who hasn't answered yet. Yes? Looks like the third one. It's a split. So that tells me they're all equal. So immediately I know that y2, y1, and y3 are all the same. All right, well, now let's notice that y1 came from, I have this part of the picture. So let's figure out what y1 is. So let's just focus on this part of the picture. What does that look like? The first one. So that tells me y1 is just g1 x2. Well, that's good. Now let's figure out what x2 is. Let's focus on this part of the picture. I've got x1 and y4 coming together to give me an x2. Which rule does that look like? Someone new who hasn't answered yet? The second one. So the second one tells me it's just the sum. So that tells me that g1 stays the same, but x2 is just x1 plus y4. Okay, I'm getting somewhere. Now I'm going to figure out what y4 is. Let's focus on this part of the picture. I've got y3, g2, and y4. What does that look like? The first one, which tells me that y4 is just g2, y3, which is the same thing as g2, y1. Because y3 is the same as y1. So, I have y1 is g1, x1 plus g1, g2, y2. Y1. I've got y1 on both sides. I solve for it. If I solve for it, I find that y1, my goal, remember, I want to get y2. Fine. So y1 is the same as y2. Well, that's equal to g1 x1 tilde divided by, I bring this to the other side of the equation, factor out y1. 1 minus g1 tilde, g2 tilde. And so even though we had a complicated looking diagram, this one, with feedback, we get this result. Straightforward. Imagine if we had to do this with algebra. The algebra would have gotten hairy, but we did it with pictures. It's much easier with pictures. There's a good reason Feynman got a Nobel Prize. He was able to do these calculations with pictures. And this is an exact calculation. By doing it with pictures, we didn't throw out anything important. We did it correctly. I also want you to notice something. In this particular case, with the CSTRs in series, the overall G is just the product of the G's. Actually, we saw that here. In this problem, the G for two CSTRs in series was just the product of the G for each of the individual CSTRs in series. They just look like this. And of course, I've left it out there. this was, I needed the KP one there. This was just a product of the two CSTRs in series. This is G1 with its KP and G2 with its KP. Exactly a special case of that. Notice the denominator, when I have no feedback, has the same roots as each of the individual G's. This G has a zero, the denominator has a root. S is minus 1 over T1. The second one has a root. S is minus 1 over T2. And the two of them together have those two roots, minus 1 over T1, minus 1 over T2. So when I don't have feedback, the stability of the whole system is the stability of all these systems together. If they're all stable individually, then they're stable together. If one of them is unstable, it screws everybody. However, once I have feedback, the denominator is different. It's not the denominator of G1. It's not the denominator of G2. It's 1 minus G1 tilde G2 tilde. It's a different denominator. It's a different stability problem. So once you add feedback, you're in a whole new ballpark. It's kind of, I don't know if there are any baseball fans here, but the Dodgers won 111 games this year. There are only 3 teams in history that won that many games since 1900. But they just lost to a team, San Diego, that won like 20 some odd games fewer than they did. Once you get into the playoffs, it's a different ball game. It's a whole new system. Once you add feedback, it's the playoffs. It's not the regular season anymore. So you may have had a system that was perfectly stable in the regular season. Almost nobody could beat the Dodgers in the regular season. But once you get to the playoffs, that stability could get lost. Once you have feedback, that stability could get lost. Or the other way around. You could have a system that without feedback is unstable, and with feedback is stable. Who knows? It's a different system, the feedback system. Are there any questions on that? Please. Go ahead.
Can you explain why the diagram 2 and the diagram 3 basically look like this?
Which is diagram 2 and which is diagram 3?
Your column of like makes sense, like model.
Oh, yes, yes.
Yeah, so the second and the third look like it's just like a mirror image of them?
Yes, yes. But the arrows are in different directions. I should have put arrows in there. So here, they're flowing together, and here they're separated. So they're different.
But why do you sum the branches in both?
Why do I sum the branches?
Why do you sum the branches in one and you don't sum the branches in the other?
Because here they're coming together, and here they're going apart.
But what would you,
Oh, so you're saying, why don't I say this is equal to the sum of those two? Think of the following system. Let's say, imagine I have, this were a flow of pipes. So I've got a blue liquid and a red liquid. If they're flowing this direction, and I combine them, I get a purple liquid. If I have a blue liquid here, and I split it up, both of these are blue liquids. How am I going to get a red liquid out of that? So that's the analogy of it. Remember, it's not like this is given from some divine being. I'm trying to represent this in a picture. I really went this way, not this way. I'm trying to represent this in a picture, so this picture makes sense because I think of the blue liquid and the red liquid. I'm trying to represent this in a picture, and I'm thinking of the blue liquid with the pipe splitting up into 2 pipes with a Y connection. So that, I presented it backwards. I presented it like this were coming from heaven, and we interpreted it this way. Really, it's the other way around. I want to represent these equations in pictures, and I made the analogy to pipe flow to know what picture to draw to represent the sum and things being equal. Okay? So again, the pictures didn't come from heaven that I then needed to interpret. The equations, I wanted to find pictures that represent these equations, and by analogy to pipe flow, I know which ones to choose. Other questions? Okay. Well, when we talked about stability, so far we looked at stability we looked in general at stability. We said, let's look at stability. It fell from the sky, little birdie told us, and gave us an n tilde over a d tilde. Or we had a g tilde and an x prime, and we had this ratio of polynomials. And then we talked about how to analyze it. And we said, things can come out. The system can be stable, it could blow up, or it can oscillate. There might be other possibilities too. There's also something called chaos, which only comes in nonlinear systems. So I'm not going to worry that much about that here. But there are many possible outcomes. And so far, the only inputs we were worried about were steps and pulses. Steps and pulses. But sometimes you have oscillatory inputs. So for example, let's say you're interested in a system that's exposed to the atmosphere. At night it gets cold, in the day it gets warm. So you get systems, if over a period of months, the temperature on the outside, if it's not well insulated, can oscillate. Or if you look at longer terms, geological time scales, winter, summer. Temperature's hot in the summer, goes down in the winter. Hot in the summer, down in the winter. And for example, there's a well-known problem that I generally solve in a fluid mechanics class, a graduate fluid mechanics class, where if you have the temperature oscillating up and down with time, how far into the ground does that temperature oscillation penetrate? And that's important. If I have water pipes in New York City, I need to put water pipes in. In the winter it gets cold. I want to put them deep enough that water doesn't freeze and the pipes don't burst. Obviously I could put them 10 miles on the ground, but I don't need to do that. So I can calculate how far that oscillation penetrates into the ground. And I just have to bury it below that so that I don't freeze the water pipes. And that's sort of a well-known problem to solve. So the point of the matter is sometimes you have sinusoidal inputs, not just steps and pulses. Now, it actually is more general than that, because if I have any arbitrary function that's a input, that's bounded, that doesn't go to infinity, that bounces around, I can write it, and this is something you believe me or not, I can write it as a sum of coefficients times sines and cosines, as long as it's bounded. And that's called a Fourier series. So just as you can write functions as in terms of a polynomial, you could write them in a polynomial approximation. If they're bounded, you can write them in terms of sines and cosines. So any arbitrary complicated input can be written as a sum of sines and cosines, and each one of them, so I need to know how to analyze sines and cosines inputs. Obviously, in the 3 minutes remaining, unfortunately, I won't be able to do all that algebra. However, we can think for a second and at least do a thought experiment. Let's say we have a sinusoidal input, but the period of that sine is 0. Well, let's say it's infinite. It takes 100 years for the thing to go up and then for it to go down. And I'm interested in what's going on today in the reactor. So what do you think the effect of a sinusoidal input with the period of 100 years has on my reactor today? Not much. To me, it looks like a constant. So at every instant in time, today, next year, 2 years from now, the system is at the steady state consistent with that constant value. That constant value may change from today to next year, and the system just thinks it's at steady state because the variation in the input is so slow. That's one extreme, where the variation takes forever. The other extreme is the variation is really, really fast. So let's say I have an input with an average of 1, but it oscillates from 0 to 2 really, really fast, 1,000,000 times a second. And I have a chemical reactor, a chemical plant, and I'm interested in what happens over 5 minutes, 10 minutes, and it's isolating 1,000,000 times a second. What do you think the effect of that is going to be? What do you think the reactor is going to see?
Just the average.
Just the average. Because, you know, it's moving up before the system has a chance to react to that. You know, here I have a stab, or here I have a pulse, and then the system reacts to that. Long before the system gets to react, it's already went down again. And before it reacts to that, it already went up. So all I'm seeing is the average. I don't see the fluctuations. Good. So those are the two extremes. What happens in between? We're going to talk about that next time. Questions?